Hello, I'm here to walk you through the political affiliation versus tax reform problem. This is a chi-squared test of independence, and that's probably the first thing you need to figure out. If you read through here, so a random sample, 500 U.S. adults were questioned regarding their political affiliation and their opinion on a tax reform bill. So what I'm seeing is, of course, I see the random, which I'm going to use later on in the conditions, but to figure out what test you're doing to begin with, think about what really happened. They went to a person and they asked them two separate questions. So they're asking them two variables. One variable, what's your political affiliation? The other one, what's your opinion? So that's two variables. And so to me, that's the tip off that it's independence and it's not homogeneity or it's not goodness of fit. If it was goodness of fit, we would only figure out one thing about the person, and then we would already have a preconceived notion about what that is, what the distribution is. So that would be goodness of fit. For homogeneity, you're asking them, actually you're recording things about them that are already kind of happened, like they're in a group to begin with. So like I know that they're a Republican or Democrat. Like I knew that about them. I didn't have to ask that about them. I just went to all the Republicans and I found so many Republicans. And then I went to the Democrats and I found so many Democrats. This, it kind of comes later. You would end up with the same chart maybe, but it's just the nuance of, did you know they were Republican before you asked them because you would put them in groups first? Or did you ask them and then you just found out they were Republican afterwards? Like this way, it would have been possible to have like two Republicans and a whole bunch of Democrats, right? Or vice versa. The other way, for homogeneity, I would probably decide ahead of time, I want to have 100 Republicans and 100 Democrats. And this would probably be 100 and 100, right? Or not in favor, but it would be 100 of these total and 100 of these total or something, right? So independence, you're asking them two questions. So you're trying to compare those two variables. Those become variables. So that's my tip off. So that's how I started. You can see right here, I will use a chi-squared test for independence. You have to state what you're doing. I had some people say two-way test, which is what you see when you do it on the calculator. Right here, you see it says a chi-squared two-way test. Yeah, it's a two-way test, but we want to know, and the AP graders want to know, is it homogeneity? Is it goodness of fit? Like, what is it? Or is it independence? So you really should say chi-squared test for independence. All right, and then I'm just going to state it. So I'm trying to do that because I want to know, I want to determine if there's an association between political affiliation and the person's opinions on a tax reform bill. I say it a couple times because I want to make sure I get it all in there. Like down here, I said U.S. adults, but up here I did not. So I just want to make sure I kind of get it all in there and say it properly. You definitely have to say it down here once. Like you got to say it. If you say it up here, you can't skip it down here. You have to say it here. Now you could have a variable and then define that variable, like A equals the association, like there is an association or something, but I think that's a waste of time. It's probably easier just to say, like for a chi-squared test, it's easier just to write it right in here. So there is no association between a political affiliation and tax reform bill opinions for U.S. adults. Put the context in there, it'll save you. Now, once I've said it a couple of times and I have it in my null, then I can kind of paraphrase the alternative a little bit. There is no association between the two, and you'll be fine. I put my alpha in there, and then we're on to conditions. Now I follow first you're supposed to check that they're counts. That's one of the things about when you get a table. If this is measurements, distances, height, weight, all that kind of stuff, you can't do a chi-squared test. It has to be counts. So I just double check that first. They are counts, yes. But then you really are going right back into IRS 10 every time, right? Almost every time. Maybe it morphs a little bit, but almost always IRS 10. Okay, so the R and the I put together. So they are independent because it was randomly surveyed. So I say it in that way. The adults were randomly surveyed, so they should be independent of each other. And then we go into the sample size, the S. So S is sample size. and the 10% condition. So I did the 10%. 500 is less than 10% of the US adult population. And then I have to do S, the sample size. So the expected counts in each cell are bigger than 5. You have to show the matrix. You have to show that this every single one of these numbers is 5 or larger. Now you can write it in its own matrix, which I did, or you can actually just write them up here next to the other original numbers. So you can write those numbers up here, but if you put it in the original table, you should mention it down here, C table, right, or C given table, or something like that. You should mention it. Now, where am I getting all this from? Well, you should just be putting this in the calculator to start with. So that's one of the first things I did, was actually do the matrix, and I did the test just to start off with, and get my expected matrix. I did all that like right off the bat, right from the beginning. So put your matrix in, right? You go to matrix and create a matrix, and then you save it. So I'm going to go here and store, right? So you're storing whatever you want it to store it as. And once you get that stored in, then when you do your chi-squared test, right, statistics, stat test, and we're going not goodness of fit, but we're doing the two-way test. Yeah, I know it says two-way test, but that's for independence and homogeneity. So you just got to be specific which one it is. Which one is it? So when you do that, you can put in whatever your matrix here, right? So I'll escape out of there. I don't need it. I already did it. And then, of course, you get your results. The chi-squared number, which you need, and your p-value, and you can see your degrees of freedom. I'm going to show all this, though, right? I'm not just going to write those 3 things down. I'm going to put a little work behind it. So when I do my work, first of all, I'm going to say my conditions are met, and I can go ahead with the test. To get the chi-squared, it's observed minus expected squared over the expected, and you sum those all up, right? So the first one, I'm looking at this 64 and subtracting this 86.6. That matches it, and then squaring it and dividing by the expected 86.6 plus ... Now, some of you were stopping there. Maybe you'll be okay with that, but I completely recommend doing one more. Do the one on the end. Just one is not necessarily showing you really got it, right? So let's show one more. Let's do the first one and the last one, right? That's a really good habit to get into. So again, take your last value, 64 in this case again, but the expected is a little different. It's 84.36. So observed minus expected squared over the expected. Add all those up, you'll get 22.5. I'm not going to actually do that and add it up. If you had a lot of extra time, though, and you really want to check your work, then maybe you could do it to be sure you did it right. But I'm just going to trust what the calculator said right here, and you should be fine if you're doing it right. Degrees of freedom. I always show the calculation. Don't just write 2. Let's show them where it came from. Show them, like you're showing off, right? Here, this is what I know. I know how to calculate degrees of freedom. So you take your number of rows, in this case 2, minus 1, which is 1. 2 minus 1 is 1. And then we take the number of columns, which is 3, and 3 minus 1 is 2. So this just comes from the fact that if I were to know like the 64 and I know what that total is, which we do, then there is no like option for me on the 138. Like here that's 190, it's 202 total, right? So if I know the 64 and I know the total is 202, this 138 doesn't have a choice. There's no freedom there. So it really only has 1 degree of freedom. The 64 could change, but as soon as that 64 were to change, this number would automatically change with it because I knew the total. So you really only have 1 variable in that direction. Same thing in the other direction. Once you know 2 of these numbers, the third one is automatic. So that's where we end up with the 1 times the 2 to get 2 degrees of freedom. All right, so then we got our 2 degrees of freedom. And we have our chi-squared. I'm going to make a graph. Now the chi for 2 degrees of freedom, it looks like this. Once you get past 2, you get to 3, 4, 5, then you get that normal curve looking thing that's skewed to the right. But this one is looking like this. And there's a video that talks about this, and I also talk about it in the community blog, or the little place where we put answers and stuff. I talk about it a little bit there and try to explain why that curve is. But you just have to like label it. So chi-square with 2 degrees of freedom, show where your 22.15 is at, and shade it in. And this is good notation. Make sure you have the probability of chi-squared with 2 degrees of freedom being greater than or equal to 22.15. That is the p-value. So I'm going to label that p-value. It comes out really small. They show us here, 0.00015. So a bunch of zeros there. And then you just have to make sure you write it properly. So since that number, 0.000015, is less than 0.05, we reject the null. Now this is important. We have evidence to suggest. A lot of people are still saying that it's true, or that there is an association, or that, I don't know, just the way you're wording it is too sure. You're too 100% about it. So this kind of putting this evidence to suggest doesn't make it sound like it's a fact and we know 100% sure. We're not 100% sure. We have this p-value. It's low, but there is a percent chance that it's that we wouldn't have rejected, right? Or that it's not true. So we don't want to say it's true. There really is an association. So we want to soften it a little bit by saying there's evidence to suggest there's an association. Okay, so that's very important. You got to have that. Now, you don't have to say association. You could say not independent. Those are backwards of each other, right? Association means not independent. No association means they are independent. So make sure you don't mess that up. And I wouldn't really mix them. Just stick with association. That's probably the easiest. So there is an association between, put in your context, between political affiliation and their opinion on a tax reform bill. And that's it. Let me know if you got questions.